Okay, welcome back. So in this video, we're going to do two more examples that involve derivatives of logarithms. As a heads up before we get started, there really isn't too much new that comes with derivatives of logarithms. It's more so just practice using our old derivative rules, especially chain rule. Okay, let's jump into the first example. So let's say that I have h of x is equal to the natural log of 3x to the fifth minus 2x, and I want to find the derivative h prime of x. So before we get started, I think you should pause the video and take a second to think about how you might find this derivative. What derivative rules do you think are involved with finding the derivative? If you want, you can work through the whole thing and find the final answer, but at a minimum, think about this and try to look ahead and imagine what derivative rules we're going to use in order to solve this problem. Alright, so my first observation is that this is going to require chain rule, and I know that because I see that I have ln of something, and that something is more complicated than just x. So I'm going to need chain rule to handle that inside function. Specifically, the inside function is 3x to the fifth minus 2x, and the outside function is ln of something, or ln of x. Then I call my inside function g, and my outside function f, just to follow along with the formula for the chain rule. And I know I'm going to need both of their derivatives, so I'll go ahead and find those now. So the derivative of g is 15x to the fourth minus 2, and the derivative of f, the derivative of natural log, is 1 over x. And just remember, the way the chain rule works is that if we have the derivative of a composition of f and g, the derivative is f prime of g times g prime. So since I see h as a composition, its derivative is f prime of g times g prime. I like to start with the inside functions, the g. So I have f prime of 3x to the fifth minus 2x times 15x to the fourth minus 2. Just a comment, I really probably should have put parentheses around the 15x to the fourth minus 2 just to indicate that we're multiplying by that whole quantity, not just part of it. It doesn't affect the final answer, but just know if you're doing this on your own, you probably want to put those parentheses in just to be super clear about what's going on. Okay, so now I just have f prime. F prime does 1 over the input, so I have 1 divided by 3x to the fifth minus 2x, and I multiply by 15x to the fourth minus 2. To finish off, I'm just going to write this as one fraction, so I have 15x to the fourth minus 2 all over 3x to the fifth minus 2x, and that's my final answer. So this method of solving, I think of it as a sort of longer version of the chain rule. We wrote out the inside and the outside function, found their derivatives, wrote out lots of steps. In practice, you might do a shorter version. I know that I tend to do a shorter version now that I have practiced taking lots of derivatives. So I'm going to go through the shorter version with you, and in my next example, we'll only do the shorter version. Specifically for the shorter version, I remember that the chain rule is the derivative of the outside function with the inside function left alone, multiplied by the derivative of the inside function. So to take the derivative of the outside function, I have 1 over x, but instead of x, I have that inside function left alone. Then I'm going to multiply by the derivative of the inside function, so the derivative of 3x to the fifth minus 2. Then the derivative of the inside is 15x to the fourth minus 2. Now I rewrite this as one fraction. I get 15x to the fourth minus 2 all over 3x to the fifth minus 2x, and that's my derivative. So for our second example, let's say that we have y equals tangent of x times natural log of x, all raised to the 8th power, and we want to find dy dx. So again, why don't you pause, think about what rules might be involved here, and maybe even go ahead and find the whole derivative on your own, or try to at least find what you think the derivative is. Then we'll come back and do it together. So here I'm seeing that we have something raised to the 8th power. We have tangent of x times natural log of x all raised to the 8th power. So I think we're going to need chain rule. And we're also probably going to need product rule, since I have tangent times log, but that'll become more obvious later. For now, let's start with chain rule. So I see the outside function as something to the 8th, and the inside function is tangent times log. So I'm going to jump straight to that shorter version of doing the chain rule. I think the chain rule, when it has the power rule specifically, isn't too complicated to do with the short version. We just bring that power down in front, the 8, we leave the inside alone, the tangent times log, and we decrease the power by 1, so it goes to 7. Then we take the derivative of the inside function. So looking at that tangent times log, even how I said it is a good indicator. Tangent times log. So this is going to need product rule. I'm just going to rewrite this with the whole beginning portion left alone, and then I'll take that product rule derivative. So I take the derivative of tangent, that's secant squared, leave the natural log by itself, and I'll add it to the opposite derivatives. So I add it to tangent times the derivative of log, which is 1 over x. So as my final derivative, and I'll do my best to say this as it's written, we have 8 times the quantity tangent log to the 7th power, multiplied by secant squared natural log of x, plus tangent x times 1 over x. There we go, we have the derivative, we did it with the chain rule and the product rule. Alright, well hopefully those 2 examples were helpful for you to get some practice with chain rule and with incorporating derivatives of logarithms into our larger derivative problems. Thanks so much for watching, and I will talk to you in the next one.